Okay, so today we're going to look at deep Q networks, and again, this is something that you will see in your second assignment and get a little bit of experience doing that. So let's just remind ourselves what are some of the key components of RL agent. You basically have the following components, right? You have policy, which is the agent's behavior function, mapping states to actions. You have value function, which tells you how good the state you're in. And you have a model, which could, basically, you can look at it as an agent's representation of the environment, right? A policy is the agent behavior, so you can think of a policy which is a mapping from state to action. Just to remind ourselves, there are deterministic policies mapping states to actions, right? Typically, if it's a discrete set of actions, pi would be, let's say, a softmax distribution assigning probabilities to each action. If it's a continuous case, which we haven't talked about yet, but we will, pi would be, the output would be like a continuous control. Right? For example, if you're controlling velocity of your drone, the output of the policy would be what's the velocity of the drone. And there's also stochastic policies, in which case, again, the probabilities here would be the probability distribution over the actions, right? So you can choose stochastically which action you want to take. The value function, let's just remind ourselves what the value function is. So the value function, you can think of it as a prediction of future reward. How much reward will I get from action A in state S? And the Q function gives the expected total reward, right? Expected total discounted reward. And just as a reminder what the Q function is, you're going from state S, taking action A, right? So you are in state S, taking action A, executing according to some policy pi, right? So with some discount factor gamma. That's the definition of the Q function, right? So if you could compute this expectation of discounted future rewards, that would be the definition of the Q function. And the value functions in the Q functions here, they decompose into the Bellman equation. We've looked at that multiple times. Just as a reminder that the Q function, you can just unroll and write up the definition of what this thing is. And it turns out to be exactly this thing here, right? By just pushing expectations inside and writing the definition. The optimal value function, we've looked at that before as well. What's the optimal value function? Well, the optimal value function is the maximum achievable value, right? So the Q star is going to be given by taking the maximum of all possible policies of Q function that you're executing according to policy pi, okay? So if you could compute this maximum of all possible policies, that would be the optimal Q function. And so once we have Q star, we can basically define an optimal policy, right? And that should be as not surprising, which is basically taking the action that maximizes this Q star, right? That would be the optimal action to take, okay? And that would be the optimal action to take in terms of the future discounted rewards that you will be getting by executing this policy pi. And formally, the optimal values also decompose into Bellman equation. Okay, so you basically have exact same point here. So the optimal action that you're taking from state, you're taking in action, the optimal one would be taking expectation with respect to all the possible states if you have a stochastic environment. So expectation with respect to the states, your reward, plus going to the new state S prime, or taking expectation for the multiple states, to the state S prime, and then executing optimal policy from that, right? So it's kind of like saying, if I'm in state and I take a particular action, I look at all possible states that I could generate by executing this action, and then I act optimally. That would be the definition of the optimal Q function. Okay? So this is just a basic review. And a lot of reinforcement learning is basically rolling around Bellman equation, right? Rolling around these recursive definitions. Okay, so informally, this is just informally. It doesn't mean that the equality is true. Just the way to think about this intuitively is that the optimal value maximizes of all decisions, right? So you're kind of basically saying, how can I act optimally at every single time step, right? This is not quite true, right? Because sometimes you might receive like a big reward, but that might be not an optimal action, because there might be some other optimal action to take. You receive smaller reward, but in the future you'll receive bigger reward. But roughly speaking, you can kind of think of it as how do you take actions so that you're maximizing your overall reward as you're proceeding forward, right? It's just an intuition for you to have what this thing is. Because sometimes when you look at the Bellman equation, you're basically saying, what does it mean? An optimal action is I look at the reward at the next time step, plus I act optimally after that. But what does it mean? Kind of like it's a loop, right? Intuitively, you can think of it as, just trying to maximize your overall reward. Now, the model itself, let's look at the model. The model can be learned from experience, right? And it can act as a proxy of the environment. So if you think about how reinforcement learning is functioning, you have an agent, that's your brain, that's you, right? You receive an observation, you see what's surrounding you, you take an action, and then the world basically gives you back a new state, right? And then once in a while, you get some rewards. Right? And this is, and the plan is going to be interacting with the model. For example, look ahead search, right? If you have the model. Okay, so let's look at the approaches to reinforcement learning. And we've looked at some of those before, but just as a reminder, there are value-based reinforcement learning. This is what we have looked at so far. So what we're going to do is we're going to be trying to estimate the optimal value function Q star, right? And that's what we've been doing so far. And that's the maximum value achievable under any policy, okay? There is a policy-based reinforcement learning, something that we haven't looked at yet, but we're going to look at in the next few classes, which is trying to find directly the optimal policy pi. Okay? So basically trying to say, well, instead of finding the optimal value and then deriving policy from it, policy-based reinforcement learning is actually trying to find the policy directly, right? Without estimating the Q functions. Even though the two are pretty much related to each other. It's just it creates a set of different methods. And this is the policy achieving the maximum future reward. This definition might be a little bit more intuitive, right? Because ultimately think of, you have a drone and you want the drone to fly around and not crash, right? Ultimately what you're interested in is the policy. I have an observation, I take an action. I have another set of observations, I take another set of actions, right? That's ultimately what you want to do. Think of it as like a classification system. You have observations, you spit out the label. Here you have an observation, you spit out the action. The controller or your agent executes the action, get the new observation, you spit another action, right? So to me, at least, this is a little bit more intuitive, right? That's as opposed to finding what's the optimal value function of being in a particular state. And then there are model-based reinforcement learning. We've talked a little bit about this, which is you building a model of the environment, right? And you can put a lot of prior knowledge into your environment, like the physics of the world, for example, and you're going to be planning by doing look ahead, using the model, right? So there are a few papers like interactive networks that are basically trying to predict what the future might look like, right? Like for example, you can build a model of the world. If I make the second assignment be really hard, I predict that 20% of you are going to drop the class, right? That's my model of the world. So I can plan ahead, right? So can you build sort of, can you incorporate the prior knowledge? I'm not going to do that, of course, but people are really good at building the models, right, of the world and interacting with the environment. So you can do planning, which is important, right? And the planning, can think of the planning as what sequence of actions I should execute to achieve my goal, right? So if you can have an accurate model of the world, you can actually plan ahead and execute a sequence of actions, right? If you have a good environment or if you have the good model of the world. If your model of the world is bad, then this is hard to do, right? Anyways, there are, as I mentioned before, there are kind of, there's model-free RL, which is what we're going to look at right now. And there is model-based RL. We'll look at model-based RL a little bit into the future. And there is still debate in the community which ones is better to use and such. Right? Both have advantages and disadvantages. One interesting thing about the model-based RL is that you can at least explain why your model is failing, right? Because you know what the model looks like, and if your predictions is wrong, then you can at least say, well, I failed because my prediction of what the world would look like is not correct, right? So let's us revisit the value-based reinforcement learning. So, and we're going to look at the model-based RL today, right? So out of those ones, we're going to look at the value-based reinforcement learning. So we're going to be working with Q functions for now. Okay, so what we're going to do is we're going to be using deep neural networks to represent the value function, to represent the policy and the model. And we're going to be optimizing the loss function by using stochastic gradient descent. So let's look at deep Q networks, which is a very natural extension of Q networks or Q learning with deep learning. And the idea is extremely simple. As we've seen before, we're going to be representing value function by Q network with some weights W. Okay? And we're going to be saying, well, for the optimal set of weights, we're hoping to approximate optimal Q function. Okay? It's an approximation, but given enough capacity in our network, the Q network, maybe we can achieve that. Okay? The way to represent Q function, there are a couple of ways. One way is to have an input into the network, the state and the action, and output the Q function. The other way, which is more commonly used, is you have a state which goes into your network, you process the state, and then if you have K discrete actions, or M discrete actions, then you are outputting M numbers. Okay? And these would correspond to Q values. Okay? So two different ways of doing it. I think this type of setting works a little bit better. Just because you process the state, you go over all of the state, and you just basically, it's almost like, you can think of it as almost like looking at the policy by saying, here's the state, you're producing a bunch of the Q values, and if you want to take an optimal action, you choose the Q with the maximum value. Okay? Notice these Q functions, there is nothing probabilistic about Q function. These are the estimation of, if you're in a particular state, you take action A, 1, what's the expected cumulative discounted reward by taking this action? And that's what you're trying to estimate. Okay? So Q learning, we've looked at the Q learning, and the optimal Q values should obey the Bellman equation. Right? So what's the Bellman equation? The optimal state, I think it should be Q star. Yes, I think it's just at the star is at the wrong place. But this is the definition of the Bellman equation. And what we're going to do is we're going to treat the right-hand side as the target. Okay? So what we're going to do is we're going to minimize the mean squared error loss by stochastic gradient descent. So we're going to say, by solving this equation, right, we're going to say that I want, this is my target, and this is my prediction. And I want to minimize the L2 distance. These equations exactly come out from, remember we've looked at the function approximation. We had a lecture on the function approximators, and we looked at the linear function approximation, and the exact same equation was coming from the linear function approximation, right? This is going to be our objective that we're going to be optimizing. Okay? At the optimal state, when this loss is 0, this is going to be equal to that, right? And ideally, if we look at these W's are the same, right? So it's the same network. So if we can achieve that, we're going to be achieving some stable local optimum. Okay? Any questions? It directly comes out from equation above, if you think of it that way, or it comes out from just looking at the TD learning and the Q learning when we looked at the function approximation. So this is just, again, a background, something, a review what we've seen before, right? And this is just as a reminder. Remember when we looked at the value function approximation lecture, we were minimizing the mean squared error between the true action value function and its approximation, right? So this thing, what we wanted to optimize, but now instead of having the true Q function, we're actually going to be replacing it by our own estimate, right? Ideally, you'd want to minimize this quantity, right? This would be the optimal Q function. You'd want to find the weight such that this is true. But because you don't have the true value function, you're replacing it with your own estimate. And this, again, comes down from doing temporal difference learning, right? Yeah. Double. So we always minimize over double. Couple of things to watch out. Look at this W and this W, right? Remember last time when we looked value function approximation, we basically discovered it was a very weird objective to optimize, right? Because we make a prediction, that's our prediction, but then our target also depends on our own prediction, right? Which creates a lot of instability and a lot of variance for these models. Because you're biasing yourself towards your own prediction. Remember, with TD error, this is not an unbiased estimate of the true Q function, right? It's just one step look ahead and your own estimate plus the reward. And that's also why, in many cases, if you're working in the environments where this R is very sparse, then yes, at every single point in time, you're just going to be trying to match these two. But there is no signal. The only real signal is coming from the rewards, right? So you need to make sure that when you're designing these problems, you are taking into account what's the reward structure, right? You can't basically build a model and say, you know, a year into the future, I'll give you a reward, right? That's not a good setting. So, we minimize this loss function by stochastic gradient descent. We can show that it converges to the optimal value using table lookup representation. So we're in a discrete setting. Your states are discrete, your actions are discrete. We can have that. But it can diverge using neural networks. And a couple of things that happen. One thing is you have correlations between samples, right? Which basically means that you're in a state, you take an action, you go to the next state. The next state kind of looks the same as your previous state, generally, right? Because you're in the same environment, you just take you know, like turn 10 degrees to the right, right? Your state doesn't change as much. So you have these high correlations between consecutive time steps. And you also have non-stationary targets, right? You update the parameters, your target is changing, which is also bad. So if you change your parameters by a lot, particularly if you're using stochastic gradient descent, your learning rate is too high, you're changing your prediction network, your Q network, your target will change a lot as well, right? So it can be very, very unstable. So let's look at how we can fix both of these problems. One way to remove the correlations, and we've talked a little bit about this, is to use experience replay, right? So you want to build a data set from agent's own experience. So imagine that, in the simulation you run your agent, and your agent basically says, I'm in state S1, I take action A1. So it could be a random action, or it could be according to some policy, epsilon greedy policy, so that you make sure that you take, the choosing of action, you always have some non-zero probability of choosing the action. You get the reward, you get to the next state. That's your data point. You are in state S2, you take another action, you get some reward, you go to state 3. That's another data point. Okay? So build yourself a table of these data points. One thing to note here is that notice that this data set doesn't depend on the policy. Right? Think of taking actions as taking random actions. Okay? There is no policy involved here. It's just a data set. So that's why it's sometimes called experience replay. It really is saying that I throw my agent in some state, my agent takes some action, what happens? You get the next state, you get the reward. I throw my agent at another state, I take the action, what happens the next state and the reward, right? So you can construct this setting. In particular, for your second homework, you'll run the simulator, you'll construct this data set, and then you're going to be sampling experiences from data set and apply the update, right? So instead of going sequentially, you're going to be sampling all of these experiences randomly, or maybe uniformly at random, which breaks down correlations, and it really helps stabilize the learning, particularly if you're doing it in online setting, right? Or you do mini batch learning. So within each mini batch, you basically always have different states, different actions. They are not correlated with each other. Okay? Now, for the second part, what we're going to do is we're going to have two sets of weights. We're going to have a set of W, and we're going to have a different set of weights called weights of the target network. Call them W minus. So to deal with the non-stationarity, the target parameters W minus are going to be held fixed. Okay? So think of it as follows. Initially, when you start your training, these weights are the same. Okay? Now you hold your weights fixed for these ones, and you do a whole bunch of updates for your Q network. Right? So your target is always fixed. It stays fixed. Once in a while, you're going to be syncing the two weights together. Okay? So after a number of updates, you're going to be saying, okay, now I'm going to set my W. I'm going to set the weights of my target network to be the same as the weights of my prediction network. So I'm going to be syncing them. In many cases, what ends up happening is you're basically using, let's see if I have the update rule. What you end up doing is you're basically saying after a certain number of updates, you're going to update these weights by saying 0.9 of these weights plus 0.1 of these weights. Okay? And then after that, you're going to be resetting these weights to be the same as these weights. So think of these weights as a slow moving weights, and these weights as just adjusting at every single update. Right? Okay? Yes. Yep, you can do it randomly. Sometimes if you have some policy, you can use the policy if it's epsilon greedy, but generally you do random actions. So you create this massive data set, and you're hoping to cover as much as possible, right? Because sometimes you're in state, you take an action, get big negative reward. You want to have that in your training examples, as training samples. Once in a while, you train it on these experience replay, and once in a while, you can generate a new data set. But in many cases, you just generate one big gigantic data set, and you do the update of these rules. So given experience consisting of state value or state action value pairs, right? In our case, it's the state action and then the next state and the reward. We're going to be sampling the state value from experience, right? If it's a value function or Q function, and we're going to be just applying stochastic update, right? And taking derivative with respect to the value function. So this is called experience replay, and the important thing here is that you're sampling these guys from your data set uniformly at random, okay? And that breaks the symmetry, or that breaks correlations. Think of supervised learning. As I mentioned, I think I mentioned before, imagine that you have 10 classes. Imagine you're updating the network for one class, and then you're updating the network for another class. You're updating the network for another class. You know, your training is going to suffer a lot. Because I give you like 1,000 examples of birds, and you're just learning what the bird is. And then after a while, I give you 1,000 examples of dogs, and you're learning what the dogs are, and you're forgetting what the birds are, right? And so forth. So you're basically trying to break those correlations. So the deep Q networks, they use experience replay and fixed Q targets. So you store these transitions in the replay memory, D. Think of it as just creating a data set. Yes, question? Evaluate. Oh, the evaluation of the training, you typically look at the overall rewards that you're getting as you're training, right? That's generally you always do, you know, your training, this is your training. You have the same set for the evaluation, which you never touch. Right? This is your test set. In many cases, you know, sometimes it's difficult to separate training from tests because you are in the environment, navigating in the environment, and so generally we'll see some examples that, you know, maybe if I learn to play one game, once I've learned it, I start at some random configuration, I play the game, and I see how much reward am I getting. Sometimes the evaluation is being done on, we'll see some examples on transfer learning. You train in one environment, you test in a different environment, or something like that. Obviously, you have to test generalization one way or another. In many cases, you create this list, you create some validation set, you can at least see what's happening on the validation set, so you're not overfitting to the training set. But the notion, again, the notion of the training set in these settings, particularly if you're in a simulation world, becomes a little bit funny because I can simulate infinite number of data points in principle, right? So I'm just constrained by how much I can store and how much I can compute. So you store these transitions. Yes? Yeah, you can do it once. You just can do it once and you store. In some cases, we'll see some examples where obviously your replay buffer needs to be quite large. There are examples where you can re-regenerate the replay buffer using your policy that you've learned so far and maybe making it epsilon greedy. So you're kind of exploring actions that you think are good actions. But in general, if your data set is big enough, you just create this replay buffer of 1 million samples, and you're learning based on that. So here you're going to be sampling random mini batches of transitions from D. Right? Again, this can be policy independent because you randomly pick state and action, get the next state, get the reward. Randomly pick state and action, next state, next reward, right? And then you compute the Q learning targets with all fixed parameters, and then you optimize the mean squared error, right? So this is called Q learning target, and this is the Q network. So this is the target network, this is the Q network. Obviously, you need to resync these parameters, right? Because ultimately you want these parameters to be the same. You don't want them to diverge too much. So again, the way that typically is happening is basically after a certain number of updates, maybe 1,000 updates, you readjust these parameters by taking a weighted average of these old parameters with the new parameters, and then you reinitialize these parameters to be the same as these ones, right? So one of the settings of W is moving slowly, update slowly, so you don't have these disturbances. Because if you have these disturbances, then let's say I have a huge gradient because I have an error. And now my network changes by a large margin by taking one gradient step. You don't want this network to change also by a huge amount. Because then at the next time step, your gradient tells you go in a different way, right? So it's almost like momentum, if you think about this particular model, right? You're kind of like changing weight slowly, and you have these other target, your Q network can change a lot, but your target network, changes very slowly, okay? And then you can use stochastic gradient descent. And this is, again, samples from your replay memory. So the two things are important here is replay memory. It greatly helps the learning. And the second one is this idea of changing the target network weights slowly, right? Holding them fixed for a certain number of updates and then, changing them fairly slowly, making them be in sync with your Q network. Okay? Any questions? These are the two key components to make basically these models work on large-scale data sets like video games, for example. Yes, question?
In general, do you see every unique tuple at least once in these models?
Yes. You always see at least once, for sure.
But you can see it multiple times.
You can see it multiple times. Generally, the way to implement things, you build this big buffer. You kind of like randomly permute it. And just take the first 100, that's your mini batch. Take the second 100, it's your mini batch. Take the third 100, it's your mini batch, and such, right? It's the way to implement it. Yep, there's another question.
Yes. How do you determine the weighted average of minus proportional time steps?
Yeah, that's another hyperparameter to choose. Like, how do you determine, how do you sync these parameters? Think of like a momentum type of an update. You do a few updates, and then you basically say the new W bar here is going to be 0.9 of old W bar plus 0.1 of these weights. So this W bar doesn't change as much. And then you basically say now reset these guys to be the same as this guy, so that now in sync. And again, these guys will diverge. These guys will catch up a little bit, and you resync. And how exactly this is done, how many iterations, what's the blending, those are all hyperparameters, right? For different problems, could be different. And again, for your second homework, you will play with these models and kind of explore, have some exploration of what they do. Generally, it's pretty hard to train these models. So it should come as no surprise to you that even in supervised learning, we always have to choose the learning rate, the hyperparameters, and can have a big impact on the performance. Here, the situation is much worse, right? Because you don't get signal at every single time step. You get sparse rewards. And how do you make sure that this is now behaving reasonably well? That's challenging. So there are like some papers basically showing that basically we have no idea how to optimize these systems, right? Like you can choose different hyperparameters and your results are much better and such. And this should come as no surprise because again, if your rewards are sparse, you have very small learning signal. And you have the deep network, so you try to deal with all the complexities in the world and such. So it's pretty challenging. And that's why compute is very important, right? You simulate billions of things across, Anyway, so let's look at the DeepQ networks in Atari. And again, once you're optimizing this, what you do is you take the derivative with respect to this guy, right? And then you backpropagate this quantity with respect to all the parameters in the neural network. So that's your standard backpropagation algorithm. If you look at this setting, this is just, it just looks like a supervised learning with L2 loss, right? You have the target, here's your prediction, update your predictions to match the target, and backprop through your neural network, or whatever function approximation you're using. So the DQNs for Atari, this is sort of like a setting again. This is you, how you're playing it. You're taking an action. The environment now, not the world, but the environment gives you the reward, which is deterministic, right? So it makes it much simpler. It's not like if you're in this state, once in a while you get big rewards, sometimes you get negative reward, and so it's not stochastic, it's deterministic. and the environment also gives you the new state. And the new state is also deterministic, not stochastic, right? So it's a much more simplified environment, which is true for lots of simulation-based environments, right? So it makes your problem a little bit easier. So in Atari settings, you basically have end-to-end learning of Q values from pixels. You have an input state, which is a stack of raw pixels from 4 frames. Your output is Q for 18 joystick positions or actions. And your reward is the change in the score for that step. Right? So if you're, the change in the score is basically, how many extra points you're getting for taking this action, which makes sense. Most of the time you don't get anything, and once in a while, you get points. Okay? So this was done back in 2014, and this was an interesting work because before that, people always were looking at reinforcement learning and looking at 2D environments and it's like checkerboards, and it was never very interesting. It's like it's a very theoretical field. When I was a grad student, people, there's a lot of theory in reinforcement learning, but at that time, it's like, yeah, you have these toy examples and you do something on toy examples. But back in 2014, basically they've shown that with enough compute and with these convolutional networks, you can actually do interesting things. And the network architecture and hyperparameters were fixed across all games. So it's the same set of hyperparameters. And if you're interested in the source code for these models, you can just basically download and train these models. So here's what they look like. These are very simple simulation environments. I mean, it's interesting how time flies so quickly. So right now, people are even thinking that this is now becoming toy. It's like an amnest of reinforcement learning, has become an amnest of reinforcement learning. If you want to test your algorithm, you test on these simple Atari games. Now people are will look at being able to do it in 3D environments, like something a little bit more complex. But you can see that you basically have a network that learns to play a lot of these games, right? So for example, here the input is the frame, the representation of the frame, and you basically have to you have to learn to to play breakout. Okay. And so what's interesting about this is that if you look at the Atari games, I think that these are all the games. I think this is the line that indicates human level performance. So for a whole bunch of games, these simple deep Q networks were doing much better than humans. Right? So which is interesting. That was shown back in 2014 that you can actually learn to play the games. And then it's interesting if you look at, for example, the breakout. Oops, sorry. If you look at the breakout here, what happens is that after lots and lots of simulations, the model basically learns to act optimally in the sense of like building a tunnel through the bricks and then pushing the ball through the tunnel and just scoring as many points as possible, right? And it can be very precise at doing it, way better than humans, with enough simulations, right? So it can discover strategies that's very hard for people to do, but these algorithms can do. The only downside is that it requires you to tens of millions, hundreds of millions simulations to learn it. So people are much more efficient at being able to learn these games much quicker, right? But if you give enough simulation to the algorithm, it will be better than a human, at least for these games, which is what's shown on this slide. Now let's look at a few extensions of this algorithm. There is something that's called double Q learning, which is you're training two action value functions, Q1 and Q2, and you're basically doing Q learning on both, with a certain caveat. You never you never basically use Q1 or Q2 on the same time steps. Yeah, I need to fix that sentence. That doesn't make sense, right? Well, you never use the Q values in the same time steps. You basically pick Q1 or Q2 at random to be updated at each step. And again, the goal here is to try to break the symmetry or correlations. Right? So for example, if you're updating Q1, you're going to be using Q2 for the value function at the next step. Right? So for example, if I am updating Q1, right, then my Q1, you're taking the optimal action according to Q1, but the evaluation is happening according to Q2. Right? So when I take the derivatives and update parameters of Q1, I'm only updating these guys. Right? So it's kind of like you have two Q values. One is prediction, the other one is evaluation. And we'll see later on there are classes of models called actor critic, where an actor takes an action, the critic is just evaluating the actor. So there are extensions of these models. Action selections can be epsilon greedy with respect to the sum of Q1 and Q2. So for example, you can choose the actions by taking the average of these Q1 and Q2 and making an epsilon greedy if you want to. This is what the double Q learning looks like. This is just one example. So let's look at how the double Q learning actually works. You initialize Q1 and Q2 arbitrarily, let's say to 0, so to some random numbers. And then you repeat. You initialize a state. And for each step in the episode, you choose an action A from S using some policies derived from Q1, Q2, for example, epsilon greedy. And this is online learning. If you want to do offline, you can just, again, like we've seen with replay memory, you can just store the data sets. You take an action, you observe the reward the next state, and with probability 0.5, you update Q1. With probability 0.5, you update Q2. Right? So you flip a coin, basically say which one you want to update, and iterate. This is something that was developed back in 2010, before kind of like people started looking at deep learning. So this is your standard double Q learning. But people also found that for deep Q networks, if you actually do double Q learning, it works really well. So for example, you have current Q network is used to select actions, and then you have older Q network to evaluate actions, right? So you can think of it, the way you're doing updates is you take an action according to your current model, current prediction model, but you do evaluation based on a different Q model, right? So there's an evaluation Q network, and then there is an action selection Q network, right? So you're maintaining two of them at the same time. But the trick is that you're picking which one to update randomly, right? Okay, and this is the action evaluator, right? So you take an action, and then you have another Q network that evaluates, and they maintain two separate sets of parameters. And if you do it that way, it's interestingly, there was a paper that basically showed that for the whole bunch of Atari games, you can actually improve substantially by using double Q learning. Okay. So for a bunch of settings, I think that this is double Q network. This is chain, this is double Q network, and just deep Q network, right? So pretty much everywhere, double Q learning would help substantially for a whole bunch of games. Okay, now there are a couple of other things to do. One of the things you can do, and we've talked a little bit about this, is to do prioritized replay. So you want to weight experiences according to some surprise, right? Or for example, you can store experience in priority Q according to some deep Q network error. Okay, so for example, here you can look at a whole bunch of pairs in your training set, right? State, action, reward, the next state. You compute this difference, right? And you can basically say, with stochastic prioritization, you can basically say, I want to be able to choose what next instance I should be updating according to this quantity, where these PIs is proportional to some error, right? So the bigger the error, the more likely you're going to be choosing this particular example, right? And alpha here is the controlling what the PI is. So that's, if it's an absolute value, it's always positive. You have some positive, you can raise it to some hyperparameter alpha. If alpha is 0, then you're recovering back the original replay memory, right? Because if alpha is 0, then you basically have uniform distribution. You have uniform distribution, you're just randomly picking up examples. The idea here is that maybe for some examples you're really bad, and some examples you're really good, so you want to focus more attention on examples where you're making big mistakes, right? Which makes sense. And again, this is done stochastically, which basically means the probability of choosing any one example from your training set or from your replay memory is non-zero, which is important. Yes, question?
Updating the errors after every update of the weights?
Yeah, so this is a good question. Generally, it would be very difficult to do it computationally. So what ends up happening is that you do it once, and you sample according to these probabilities for a whole bunch of updates, and then you redo it again, right? And you as a model have to kind of like see how much compute versus how much, this helps. So obviously it's like being able to compute these things is computationally hard. At the same time, what people end up doing is they basically saying, okay, here's my example. I have to compute this quantity anyways, because I need to compute the gradients. So I'm just going to be maintaining this list of what I'm seeing. Once in a while, you still have to do the whole sweep, because there's some probability of choosing some examples can be very small, but the errors could accumulate after a whole bunch of updates. So you have to do once in a while the whole sweep. Yes, question? In supervised learning, yeah, I think that people have tried looking at supervised learning, something called curriculum learning, right? Like people looked at the errors and tried to figure out. But at the same time, in supervised learning, it's much easier. It's a much easier task. So. The what? No, if R is 0, then basically you just have to match this according to this, right? So it depends how the matching is happening. It doesn't have to be big or small. So alpha key determines how much prioritization is used, and alpha 0 corresponds to uniform. And there is a paper that you can look that basically studied this effect of alpha for the whole bunch of settings, and in some settings it helps a lot. Right? So that's one example. Yes? It might. Because if there are certain parts in the environment where you're making a whole bunch of mistakes, then yes. But at the same time, that's okay. Like let's say you're navigating in the maze, you're solving some task in one particular set of states, you're really bad. So just focus your attention to fix that, right? And then you're recovering. But yes, it can. It can break the correlations back. So again, it's not a bulletproof technique. It doesn't work all the time, but that's one example to do. Obviously, I always joke is that if you set alpha to 0, you recover your own algorithm. So there's always exists some alpha where you'll do better, by definition. Right? This is one more hyperparameter to tune. So obviously, if you tune this hyperparameter and your results are like epsilon better, then it's not worth it, right? Because it's probably due to like noise and you choosing this hyperparameter. Another class of models is called dueling networks. And what you're going to be doing here is you're going to be splitting Q network into 2 channels, and there's a corresponding paper you should look at. So there's an action-independent value function V. Notice that V doesn't depend on the action. And there's an action-dependent function called advantage function, A. Okay? So you can think of Q function as being decomposed into V, which is the value of the state, plus the advantage function. Okay? Or if you think of it differently, the advantage function looks at the Q minus the value of the state. Okay? So you can think of the advantage function as kind of a normalizer. Right? Imagine that I'm in a particular state, and it's a really, really good state. If I take action A, I get big Q value. I take action B, I get big Q value. Life is good, right? But it's kind of, maybe if I subtract the value of the state, because the state is so good, then maybe, I'm just basically normalizing it, right? If you think of it that way. So the advantage function, sometimes people look at the advantage function as what we need to optimize. It's almost like subtracting the mean or normalizing your Q values, right? Or sometimes you might be in a situation where the value of the state is really bad. You take action A, you're going to die. You take action B, you're going to die. You take action C, you get like big penalty. So all your Q values are terrible, right? But at the same time, you still want to take the good action. And so if you subtract the value of the state, which would be the average of all of those actions, right, essentially, then you're kind of normalizing this quantity. So it's much easier to deal with. Yes? Yeah. This is exactly, we'll see later on, this is exactly provides the variance reduction, as a way of reducing the variance of your estimator. Yes, we'll see that. But this is an important thing to notice, this advantage function, okay? And in dueling networks, there was a paper in 2016 that basically said, well, what we're going to do is we're going to actually create a new architecture where one piece is going to be the value, the other piece is going to be the advantage function. So part of the network is going to depend on the action, the other part of the network is not going to depend on the action, right? And we're going to add them up to come up with the Q function, okay? So if you think about this way, right? Remember when we looked at the Q values, you have a state, you go out and you produce like a bunch of Q functions. Think of the value of the state as another component, which is the same for all of the Q functions, right, when you're making predictions. So there is something that doesn't depend on the action. It's almost like a bias, if you think of it that way, in a neural network. And you have something that depends on the actions. So it's a new kind of architectural design. And what's interesting is that this paper basically showed that what the value does, the value function actually learns to pay attention to the road. Like somehow the value function basically says, oh, should I be turning left into the future? Should I be staying on the road? That's the value of the state. Whereas the advantage stream, the advantage function, which depends on the action, pays attention only to when there are cars immediately in front. Because you want to take an action, avoiding action, right? So, for example, the advantage function over there was pretty much 0, right? And you can think of it, sure, right? Because if I'm in this situation, like look at this situation. If I go left, if I go right, does it matter? Doesn't matter, right? Nothing's going to happen. Whereas here, if I go left, I'm going to hit this car, right? Which matters a lot. So the value function is kind of like, for this particular example, says something, maybe a little bit globally of how good the state is and where the road is, whereas the advantage function is really paying attention to what's surrounding you, which was kind of an interesting result. And what they've shown is that, again, on a whole bunch of examples, again, games, this dueling network was improving by substantial margin. There are some examples where it was hurting, right? But there's a whole bunch of settings where it was helping. Okay? Finally, what I want to do, and later on we'll talk more about this, but there is one interesting thing that you can do is you can say, can we train a single network to play multiple games at the same time? Right? So building a single model which is not game specific but can play a whole bunch of different games at the same time. Right? So it learns some generic features across all different games and learns to execute actions. And you might ask, why do you want to do that? In principle, if I wanted to play the breakout optimally, I should build game-specific network, right? Or if I want to play this optimally, I should build game-specific, because I have infinite data. the nice thing about simulations is that you have infinite data. You can simulate whatever amount of data you want. But one interesting thing that you can do is you can take this network and then learn to play a new game much faster. And this is useful for transfer learning tasks, right? Here's an example of if you initialize at random, in this case after like a few million frames updates, which is still a lot, the random policy just basically moves forward. So you can see like this plane, it just goes forward. It just still has no idea what's going in the environment. So the actions will always move forward, shoot once in a while. Whereas a model that leverage some information from previous games can actually, move around, and it basically learns that shooting things is a good thing, right? From previous games, right? So you basically might as well shoot things, right? Obviously, that might be bad transfer. There are some settings where the transfer is not so good. Like for example, if you're at the edge of the cliff, from previous games, you're learning that jumping off the cliff is a bad idea, right? Because you end up dying and you have big negative reward. But if there is a new game where jumping off the cliff is a really good idea because you're going to the new level or something like that, then this transfer stuff will basically fail, right? Because the model will say it's a bad action from my prior experience or from my prior knowledge, right? It might take a lot of effort to overwrite that prior knowledge. But nonetheless, you can build these systems where, and there is a lot of research happening in the space of how can you build something in one environment, transfer it to the new environment, right? Obviously, in the settings where you go in the simulation, you transfer it to the real world. Like, how well can it work? Yes, question?
If you're training on multiple games and multiple different tasks, do you have to normalize your...
Oh, yeah. So there are, I haven't really spoken. We'll have a separate lecture on the transfer part. Yes, you have to normalize, and you have to, because sometimes the reward structure for one game is like in the millions. The reward structure for another game is like in, 1 or 2 and such, right? So the scales can be quite different, so you have to normalize, yes. All right, so homeworks I do on Monday, talk to TAs, make sure you're not late for handing in your homeworks, and next homework is going to be out on Wednesday.